This is John Black, Super Chemist. This video is part of two playlists, one called New Updated Frames of Reference, the other called New Updated Time and Time Dilation. And this individual video is about understanding what length contraction is. Relativistic effects are only noticed at high speeds. And some people say that time dilation and length contraction are two examples of relativistic effects. But speed is length divided by time. So this can be, all these relativistic effects can be explained by time dilation or length contraction or both. But one is relativistic and one is not. And the reason why they want to have this length contraction is because your photon clock, when it's laid longitudinal like this, it doesn't work out the way they say. See, if you're going this way, your velocity, and your photon clock is like this, yeah, it goes up and down, up and down. Each second, you can see this side is the same length as this. But what about you have two clocks on your ship, and this clock is laying on its side. Now it bounces up, but the first second here is longer than it should be because you're moving this way. This top plate is moving as the photon is trying to catch it. And the opposite on this, when it hits this plate and it goes back down, the bottom plate is moving into it, so you don't get a long line like you get like this. You can see this does not match up with this. So they explain it away with length contraction. But if you use classics physics, you can explain it away by saying that you need two-way communication for physics to happen. You can see that this second and this second, they're even. Yeah, they're different than this, but when you line them up together, if you're talking about two-way communication, they're the same exact line. That fixes your problem. It's not that you have length contraction, it's that you need two-way communication in order for any physics to happen. See, length contraction means your viewpoint is contracted, not your length. Your frame of reference has contracted your viewpoint, and therefore you contracted the length. But the length is not really contracted. And this is something that happens at 0 miles an hour. Every velocity that you can think of will give you length contraction. So this means that it's not a relativistic effect because it happens at slow speed. You never notice time dilation when you're going slow, right? Relativistic effects takes place if you're moving 1 mile an hour or not, no matter how slow you're going. But you won't never notice it unless you're moving fast. And that's what we mean by it. You only notice it at high speeds. You can't notice it at slow speeds. Here, length contraction, you can notice it at 1 mile an hour. You can notice it at 0 miles an hour. And this length contraction thing, saying that the length contracts, they're basically saying the entire universe contracts in a moving frame. And we must live all in different universes, because in your universe, if you're moving, the length is contracted, but in my universe, it hasn't contracted because we're all living in different universes. This is insane. You can explain literally everything that length contraction, and basically it's about this, but everything that they say about length contraction can be explained with time dilation because it's all about speed. And speed is length per time. So you can pick one or the other, you can combine them. Mathematically, yes, you can say it's length contraction. But a mathematical construct does not mean it's reality. Now before we move on to the next whiteboard, I want you to remember my postulates. What's two of my postulates? One is, if you are standing here and something is moving this way in the x-axis, the length contracts. The length on this moving object will contract. What's my other postulate? If you are here and there's an object in this same x-axis as you, if you are in the same x-axis, you see zero length. It doesn't matter how fast you're going. You can be standing still when it don't matter. This is why we know length contraction is not a relativistic effect. It's just, and not only does it prove that it's not a relativistic effect because it happens at slow speeds, since it does happen at slow speeds, we can actually look and see what's actually going on. So let's do that on the next whiteboard. So now we know that length contraction is not a relativistic effect because it happens at 0 miles an hour. But what is it exactly? Let's do an example here. This is a door. This is you standing right here. This red line is your line of view. You see how it's always straight because you're looking at the door. And this black line is the plane of the door. That's the axis in the plane of the door. You can notice here, I'll see the door is 3 feet wide. I have a 90-degree differential between my line of view and the plane, or the x-axis of the door. Now we open the door, so this a little bit over, whatever, and you're standing here. Now the plane of the door, the x-axis of the door, has now rotated, and you can see that your line of view and the door has the angle in between went down to like 70 degrees, and the length contracted. Then you open the door even more. Now the plane of the door, the x-axis of the door, is 45 degrees angle difference from your viewpoint, and the door looks even more contracted. Then you open the door up so that you are in the same plane as the door, the same x-axis. The door has 0 length at that point. You can only see the thickness of the door. Try it. Open up a door, stand right, 2-3 feet in front of it, and you will notice that you see the thickness of the door, but you don't even see not even a sliver of the front or the back of the door. You can only see the thickness. It has 0 length on the front and the back. So you can see it's not that your length contracts, it's that your perception has been rotated and therefore contracted. And since your perception is contracted, the length looks contracted. But this is just a mirage or whatever. And if you want to believe in length contraction, you have to believe that when you open a door like this, that the door literally disappears and the length literally contracts. Because why do you don't believe it here and you do believe it at high speeds? This is length contraction, literally. Let's look at another example of length contraction. And these aren't analogies. These are literal examples. This is length contraction. So do you really believe that the door disappeared, the length literally contracted, or was it your viewpoint was contracted because you rotated the door's frame of reference, so your viewpoint got rotated and contracted? So here you have the same guy standing still. The door is moving. It's not rotating. It's moving to the x-axis. And again, what did I say when it happens? The length gets smaller and smaller and smaller. Just like up here, when you're in the same x-axis plane, yeah, you get 0 length. But as it moves more in the x-axis, the length contracts more and more and more. And you can see right here, if I draw a line from the midpoint down to where I am at, and a line from this side of the door and that side of the door, they got to be parallel, right, those lines. So they would come down to here, and you could see, I would see the whole width of the door at 90 degrees. When my viewpoint and the plane of the door, its x-axis, when it's at 90 degrees, I see all of the door. How about over here? I draw a line from the midpoint down to this dot, and then I know this line and this line, they have to be parallel. But look at the distance in between those lines now. This red line has a big distance. Look at this one. It got smaller. And then what happens when the door moves even more? I do from the midpoint down to me, and then I do 2 parallel lines that start from here and here. You can see the distance here. It's the length has contracted. Then it moves even more. It gets contracted even more. But what's happening? You can see this is my line of view. This is the x-axis the door is in the plane the door is in. It's 90 degrees. Now look, here's the x-axis of the door. Here's my viewpoint though. My viewpoint has been rotated. It hasn't really been rotated, but well, it has, because the door has moved, and that rotated your viewpoint of the door. And you can see the angle would be smaller. The same, just like up here. Then the door moves even more. Now I do the same thing. A line from midpoint to my eyes, and then I do two parallel lines that start at each side of the door. You can see the length is even getting smaller, and it gets smaller and smaller the more the door moves into the x-axis, because you're rotating, just like up here, you rotated the door. Here you're rotating the actual, moving the door, but that rotates the viewpoint just the same way. You go 90 degrees, 70 degrees, 30 degrees, 20 degrees. This is, now is the door length contracted, or is your viewpoint contracted because you rotated your viewpoint? And this is why you see length contraction from both sides. The moving door will see this being length contracted. This guy that's standing still will see this being length contracted, because it's about the angle. The angle of your viewpoint in the x-axis is what determines the length that you see. Not the length it is, the length that you see. And you can see this angle right here will be equal to this angle. If you draw the midpoint from here and do the same thing in reverse, you get the same angles. So you get the same length contraction. You can see if these two lines are parallel, this right here would be equal to this. That's how parallel lines work when you put a line through it. So this guy will see this length contracted, and this guy will see this length contracted. Now, if the guy's moving at the half C, what do you expect that length is going to happen there? Yeah, it's moving in the x-axis. You're standing right here. Yeah, of course it's going to get smaller and smaller and smaller. That's just common sense. When you open a door up, it gets smaller and smaller and smaller. It's not, a child knows this. Remember, velocity is distance over time, but they do the same thing with the time part of it. The time dilation is real, but their interpretation is just crazy. First of all, you can't. It's not a dimension. You can't put the time dimension on this graph without removing one of the spatial dimensions. That in itself proves that it's just a mathematical construct. But if you have this, we know the scenario. This rocket's going 0.8c. 4 light years to the nearest star, and this is you, and now you're going in a spatial dimension, so you're going in the time dimension less, and so now you have two component vectors, one of time and one of space, and this is your real component, resultant vector, what everyone else would see. They'd see 5 years. Yeah, and if you think the sun revolves around you, then yes, this is the way to go. But the classic physics says this is the photons vectors. You started moving. The photon, doesn't it just move in the y-axis motion if you're just standing there? Then you start moving to this other star. Now the photon has to move in the y-axis and the x-axis. That's two spatial components of not you, the photon. And this is the resultant vector. So you are only moving in one dimension. The photon is moving in two dimensions. The x and y dimension both are spatial. None are temporal. If it was 4 light years, your photon would have moved 5 light years. So you do this Pythagorean's theorem and find out what your standing still second was, because this is your moving second. Moving second was 5. Y is 3, so your gamma is 5 over 3, 1.67. See, you can move, that photon can move forever in the x-axis. How is it going to hit the other plate? It bounces down to here. Now, let's say it only had x-axis motion. It can move forever. It'll never hit that plate. Same with if it's up here and all it had was x-axis motion. It could never help time or physics proceed. Only the y-axis motion helps time and physics proceed. So the 3 years the photon went in the y-axis, that motion helped time and physics proceed, right? It helped the photon bounce back and forth in between the plates. But the 2 years was wasted keeping up with you moving in the photon had to keep up with you moving in the x-axis. That was 2 years. That's your time dilation. It's not that you're moving less through the time dimension. There is no time dimension. You can't. You'd have to remove one of the spatial dimensions to put it on the graph. It's just a mathematical construct. But see how they manipulate everything. Why are you people believing in this magic? What's funny is none of you have heard the classic explanation from a classic physicist. You've only heard the explanation of a classic physics from a quantum physicist. That's kind of like saying, well, I know what happened between this rapist and this rape victim because I got the story both sides from the rapist. No, you go to the other side to get the other side of the story. Otherwise, you have only listened to one side of the story.